We start our study of physics with kinematics, which is a study of motion. And although he doesn't actually use that particular term, everything that we're going to be discussing in the next several modules all has to do with motion. In this particular module, we're looking only at motion in one direction. And in order to start talking about this motion, we need to set some definitions. And the first one we need to talk about is the difference between a scalar quantity and a vector quantity. A scalar quantity includes no directional information with it. So as an example, you would say 3 meters or 50 yards. A vector quantity, however, includes directional information in it. So instead of just 3 meters, you would say 3 meters north. Or instead of just 50 yards, you would say 50 yards towards the goal line so that you know precisely which direction you're talking about. So a lot of the different quantities that we're going to be discussing here, we're going to define as either being scalar or vector. So we're going to start a chart so that we can make sure we can keep them all straight. The first two that we're talking about are distance and displacement. So distance is basically how many steps did you take, how many miles did you actually get on those tires today, how much distance did you actually cover. Displacement, though, is different because displacement talks about how far you are from your starting point. So, in other words, if you get on your bike and you ride 2 miles down the road and then you ride 2 miles back, your total distance would have been 4 miles, but your displacement was 0 because you ended up right back where you started from. Okay, so that's going to be the difference between distance and displacement. Also, if you're asked for a displacement, you always need to make sure that you're putting a direction with that if there has been a displacement. We're going to look at example 1.1 from your book, and probably one of the biggest things that you'll hear me say over and over and over during the year is draw a picture. And don't draw a little bitty picture, draw a big picture so that you can really get your measurements in there, you can diagram it out, and you can really see what's going on well in what the problem is telling you. So, example 1.1 says a child is 5 meters away from a wall and rolls a ball towards it. The ball hits the wall and bounces back, rolling 3.3 meters before coming to a halt. What is the total distance covered by the ball, and what is the ball's displacement? I tend to work a lot of problems on video because I know that it can be difficult to read an explanation in the book and completely understand what the author's trying to get across. Sometimes it's easier to hear it than it is to read it. So, if you look at the diagram, you don't have to draw a diagram nearly as pretty as the one that's in the book. I draw lots of stick figures. You'll probably laugh when you see my birds and my airplanes because they don't look anything like it. But the point is that you've got something represented on paper so that you can see what's going on in the problem. So here's the child, here's the wall. She's rolling the ball. We can put a ball in there. The problem says that the ball rolls 5.0 meters towards the wall or away from the child. And then when it bounces back 3.3 meters away from the wall or toward the child. Now, the total distance which we are asked to find is pretty easy because that's just how many meters did the ball actually cover. So if it went 5.0 meters towards the wall, and then it bounced 3.3 meters back from the wall, that will give me a final distance of 8.3 meters. Okay, that's how much space the ball actually rolled over in its journey. Displacement, though, is something different because displacement says where did the ball end up in relation to where it started? And this is where positive and negative numbers come in very handy when we're trying to calculate displacement. When you choose which direction is positive and which direction is negative, it is completely arbitrary. It does not make any difference. When I wrote my numbers up here, I chose to make towards the wall positive and back towards the child negative. You could have done it the other way. You could have made this number negative and this number positive. The only thing is that you've got to make sure that you keep in your head straight as to which direction is which, so that you know what that negative sign means when you get it in your final answer. So if I'm asked for the displacement, I need to make sure that I include those positive and negative signs. So the displacement goes a positive 5.0 meters, and then it goes a negative 3.3 meters back from the wall. So if I have a positive 5 plus a negative 3.3, that's going to give me a positive 1.7 meters. One other thing that I just want to go ahead and point out here right now that I am a big stickler about is when you answer a question, you need to make sure that you put units after any number that you write. If you don't put units on it, that number is meaningless. So if you just say the answer is 1.7, I'm going to say 1.7 what? 1.7 meters, 1.7 feet, 1.7 miles, 1.7 apples, 1.7 what? It has to be 1.7 something. So you need to make sure you put a unit after it. And for displacement, or for any vector quantity, as we'll see as we continue to go through the chapter, I not only have to have a unit after my number, but I also have to have a direction after my number. So the positive sign tells me that the final displacement was towards the wall or away from the child, and it doesn't really make any difference which one of those you put, as long as you put one or the other. So I'm going to say 1.7 meters away from the child, so that you know where the final displacement was. So the final displacement of the ball is going to be right here, is where that ball actually ends up. So from that point, we're looking at this distance from here to here. This is the starting point, this is the ending point, so this is the displacement. I'm not worried when I find displacement about how far it's traveled or what kind of circuitous path it may have taken in the process. I'm only interested about where it started and where it ended up, okay? Let's try doing one more problem like that, one that's a little bit different. And let me make some space up here so we've got room to draw. Alrighty, so this problem, I want you to picture this in your head, and we'll draw a picture. You have a person standing on a cliff, and the person throws a piece of bread up in the air, and it goes 6 meters up into the air, and when it comes back down, a bird catches it after it's fallen 2 meters below the cliff. So let's draw a picture as to what that looks like. So here's the cliff. Here's my person standing on a cliff, and this person throws, we're going to assume that this right here is our 0 mark, okay, just for matters of simplicity. This piece of bread that this person is throwing goes 6 meters up in the air, and then it falls back down, and the problem that I read said that a bird catches it after it has fallen 2 meters below the cliff. And so over here you've got this bird, and the bird, I guess he needs a beak. The bird is going to come over here, and it's going to catch the piece of bread right when it falls right here, okay? Now, just pointing out, this is not an artistic bird. It doesn't have to be. You just have to be able to get a picture so that you can see exactly what is going on in the problem. So, piece of bread goes up, comes back down. When it goes 2 meters below the cliff, the bird catches it. Now, had I not drawn a picture, what tends to happen in a problem like this is that you catch the 6 meters up and you catch the 2 meters below the cliff, but you forgot that the bread had to come back down again. And so a lot of times, if I ask for the distance that the bread traveled, in a problem like this, I'll get a student go 6 meters up, 2 meters below the cliff, 8 meters. Well, but it's not, because again, the bread had to come up and it had to go back down. And when I draw that picture, it's very easy for me to see that. So my distance then is 6 meters up plus 6 meters back down to the starting place plus 2 meters below the cliff line. So that's going to give me a total distance of 14 meters. Okay, now how about displacement? Well, if I want displacement, I really need some positive and negative numbers on here. Okay, so in that case, I'm going to make the upward direction positive. And again, it doesn't have to be positive. You could make the upward direction negative. I just chose to make it positive. So then I'm going to make the downward direction negative. So it went down 6 meters to get to the level of the cliff, and then it went down another 2 meters, so make this one negative also, to get below the cliff. So the displacement then is going to be a positive 6 meters plus a negative 6 meters plus a negative 2 meters, and that will give me a negative 2 meters is the final displacement of the bread. Now, displacement also requires a direction. The negative sign tells me that it's below the cliff, and so that's what I'm going to put in my final answer. The displacement is 2 meters below the cliff. Okay? Now with this in here, I don't need this negative sign in here anymore because I've got this direction in here. And so that's why I'm going to take off the negative sign. If you leave the negative sign on there and assume that that's going to tell me direction, then you also at some point have to tell me how you've defined your positive and negative. So it's probably easier, instead of assuming, like on a test, that I'm going to know which one was positive and negative, what you actually need to do is take that negative sign off and then say 2 meters below the cliff, or 2 meters towards the child, or whichever direction it would happen to be. So I actually want to write that out into words. Okay, so scalar and vector quantities, and make sure that you include direction anytime you write a displacement, and big pictures whenever you work a problem.